Right now, everything you can see, every star, every galaxy, every planet this screen, your body, was once packed into a space smaller than a single atom. No time, no space, no before. And then, in a fraction of a second, that changed forever. Today, we're breaking down the Big Bang Theory, what it actually says, what it doesn't say, and why almost every scientist on Earth accepts it as our best explanation for how the universe began. Let's get into it. First, let's clear up the biggest misconception right away. The Big Bang was not an explosion. There was no bomb going off in empty space, no fireball expanding into a room that was already there. That image is everywhere in pop culture, and it's just wrong. The Big Bang describes something much stranger, the expansion of space itself. About 13.8 billion years ago, the entire observable universe was compressed into an incredibly hot, incredibly dense state. Then it began to expand rapidly at first, then more gradually, and it's still expanding today. Galaxies aren't flying apart through space like debris from an explosion. Space itself is stretching, carrying galaxies along with it, like dots drawn on a balloon that's being inflated. That distinction matters. It means there's no center of the universe where the Big Bang happened. It happened everywhere all at once, because everywhere is what the universe was. And here's the part that trips people up the most. The Big Bang Theory doesn't actually claim to explain what caused the universe to start, or what happened at the very first instant, time zero. What it explains, extremely well, is what happened after that. How the universe evolved from a hot, dense state into the cosmos we observe today. So what actually happened in the beginning? In the first tiny fraction of a second, we're talking a decimal point followed by 32 zeros, the universe went through an event called cosmic inflation. Space expanded at a rate far faster than the speed of light. Not particles moving through space faster than light, that's forbidden, but space itself stretching at an almost unimaginable rate. After inflation, the universe was still unbelievably hot, trillions of degrees, and filled with a soup of fundamental particles. Quarks, electrons, photons, all slamming into each other too energetically to form anything stable. As the universe expanded, it cooled. And cooling is the key mechanism for almost everything that follows, because different structures can only form below certain temperatures. By about 1 microsecond in, it was cool enough for quarks to bind together into protons and neutrons. By about 3 minutes in, protons and neutrons started fusing into the nuclei of light elements, mostly hydrogen and helium, with just a trace of lithium. This process is called Big Bang nucleosynthesis, and it's one of the theory's biggest triumphs, because we can calculate exactly how much hydrogen and helium should exist if this model is correct. And when we look out at the universe, the ratios match almost perfectly. For the next 380,000 years, though, the universe was still too hot and dense for atoms to fully form. Electrons zipped around freely, scattering light in every direction. The universe was essentially an opaque fog. Then, around 380,000 years after the beginning, something changed. The universe cooled enough, down to about 3,000 degrees Celsius, for electrons to finally combine with protons and form stable, neutral hydrogen atoms. This moment is called recombination, and it's one of the most important events in cosmic history because once atoms formed, light was finally free to travel. The fog cleared. The universe became transparent. That light is still out there. It's been stretching and cooling for 13.8 billion years, and we can detect it today as microwave radiation coming from every direction in the sky. Scientists call it the cosmic microwave background, or CMB. This is, honestly, one of the most important pictures in the history of science. It's a snapshot of the universe when it was only 380,000 years old. The tiny temperature variations you see in that image, fractions of a degree, are the seeds of everything that came later. Every galaxy, every star, every planet grew from those small density differences. The discovery of the CMB in 1965 is what turned the Big Bang from a theory into the leading theory. Two radio astronomers, Arno Penzias and Robert Wilson, picked up a strange background hiss with their antenna that they couldn't get rid of no matter what they tried. It turned out they'd accidentally detected the afterglow of the Big Bang itself. They won the Nobel Prize for it. After recombination, the universe entered a long stretch scientists nicknamed the Cosmic Dark Ages. There were no stars yet, just spreading clouds of hydrogen and helium gas, slowly being pulled together by gravity in the denser regions left over from the CMB's ripples. Over hundreds of millions of years, gravity did its slow work. Gas clumped. Clumps grew denser. Eventually, in the densest cores, pressure and temperature climbed high enough to ignite nuclear fusion, and the very first stars switched on. This period, when the universe's first light sources appeared, is called the era of reionization. Those first stars were massive, blue-hot, and short-lived, and their radiation began stripping electrons off the surrounding hydrogen gas again, lighting up the cosmos. From there, gravity kept building on smaller and smaller scales. First-generation stars collapsed into black holes and seeded new stars. Gas and dark matter clumped into galaxies. Galaxies clustered into groups, and groups into the vast cosmic web of filaments and voids we see when we map the universe today. Every heavier element, the carbon in your cells, the oxygen you're breathing, the iron in your blood, was forged later, inside the cores of dying stars and in the explosions of supernovae. The Big Bang made hydrogen and helium. Stars made the rest. Now here's the question that actually matters. Why do scientists trust this story? What's the evidence? Number 1. The expansion of the universe. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. If you run that expansion backward like a film in reverse, everything converges toward a single point in the distant past. That's the first major clue. Number 2. The cosmic microwave background, which we just covered, the leftover glow from the early universe, sitting exactly where the theory predicts it should be, with exactly the pattern of ripples the theory predicts. Number 3. The abundance of light elements. The Big Bang model makes a very specific, testable prediction. Roughly 75% hydrogen and 25% helium by mass, produced in the first few minutes, with only trace amounts of heavier light elements like lithium. When astronomers measure the actual composition of the oldest, most pristine gas clouds in the universe, the numbers line up remarkably closely with the prediction. Number 4. Large-scale structure. The pattern of galaxy clusters, filaments, and voids across the universe matches computer simulations that start from the tiny density ripples seen in the CMB and evolve them forward using gravity. The universe's structure looks the way the model says it should look. 4 independent lines of evidence, each discovered separately, each pointing to the same conclusion. That's why the Big Bang isn't just an educated guess. It's a model with genuine predictive power that keeps getting confirmed by new data, including recent observations from the James Webb Space Telescope peering back at some of the earliest galaxies ever detected. Now, to be intellectually honest with you, the Big Bang theory has real limits, and good scientists are upfront about them. It doesn't explain what caused the initial expansion, or what, if anything, existed before. Some physicists argue the question doesn't even make sense, since time itself may have started at that moment. Others explore ideas like eternal inflation or cyclic universes, but these remain speculative, without the same mountain of evidence backing the core Big Bang model. We also don't fully understand dark matter or dark energy, the mysterious components that, according to our best measurements, make up about 95% of everything in the universe. We know they're there because of their gravitational effects, but we don't know what they actually are. So the Big Bang Theory isn't a complete theory of everything. It's a remarkably well-supported description of how the universe evolved from an early hot, dense state and an active, evolving area of research at the edges. So next time someone pictures the Big Bang as some cosmic explosion going off in the middle of nothing, you'll know the real story. Space itself stretching, a fog of particles cooling into atoms, the first light of the universe still detectable right now, all around us, in every direction you look. We didn't just learn about the universe's history. In a very real sense, we live inside the evidence for it. If this helped the Big Bang finally click for you, hit subscribe. I'm covering black holes, dark matter, and the James Webb Space Telescope next. Drop your questions in the comments, and I'll see you in the next one.